Sorry, I need to solve now technical problems. Okay.
Monday.
Just please wait. I will try to solve this problem. Doesn't work. Okay. Okay, can you see my screen?
Yeah.
Okay, so today we will continue to work with a multi-component model of the universe, and again I will remind you that it means that we consider the model of universe which consists of some components which play essential role, or we understand the role in the additional and the sum of the energy density. So, and this influence on the dynamical evolution of the universe. So, and we finished here. We spoke a little bit about lambda CDM model. What is it? It's exactly correspond to lambda CDM model, which says that this is dark energy with lambda term, and dark matter, which we consider as a cold dark matter. So, and again, I would like to say that cosmology now is a very important part of the physics, not only astrophysics, astronomy, because only cosmology now, in principle, only cosmology, we can say like this, can tell us the additional information about verification of dark matter particles, which are important also for develop of the physics of elementary particles. Sorry, I need to put some energy to my device. Okay. Okay. So now we obtain Friedmann-Lemaitre equation. Friedmann-Lemaitre equation in this form, and now we will start to investigate what this equation can tell us. So again, so this is important point, yes, that I will write here. We already put here. So this is a point that now the energy density consists of three components, three global components. So non-relativistic matter, and lambda constant. And now we can put, since we already obtained the dependence of energy density on scale factor, we can put it in, I will write like, I will put here the frame. So we can put it in our equation, Friedmann-Lemaitre equation, to see what finally we will have. And again, I want to remind that we already used this this notation that omega, which is a relative density, this is now consists of omega, let's tell me omega, which is a function of t, omega radiation, which is in principle function of t, plus omega matter, it's non-relativistic matter, plus omega lambda, which is constant. So, and where I can put that to define that radiation, omega radiation, this is epsilon radiation divided on epsilon, how we call it, C, okay, critical. Also omega matter equal epsilon matter divided on epsilon critical, and correspondingly omega lambda. So this is we call relative density. Relative density. Energy density or density, it doesn't matter because we consider the ratio between energy density and critical energy density. So also, so if we will now put and consider Friedmann-Lemaitre equation, let's write it in the first here. Okay, so h square divide on h square, h0 square. Let's work on this. Okay, so equal omega plus uh, 1 minus omega 0 divide on a square. So of course we need to put here the function of t, okay, like this. So you can see that equation really became looks very simple, this equation for the evolution of the universe. And now, taken into account the fact that relative density of the universe consists of 3 components, we can, and we know that from this one, we can see that now let's write here omega, sorry, I just need to solve. Okay, omega r equal omega r0 in the present time divide on a4. So we found this before, and this is relativistic. Let's call it relativistic matter. Omega m equal omega m on the present time a in third power. This is non-relativistic matter. And omega lambda equal, doesn't matter, omega lambda 0, and this is constant. This is lambda term. So let's put, and all together we consider as omega equal omega r plus omega r plus omega m plus omega lambda. So let's put it in Friedmann-Lemaitre equation, and we will have h divided on h0 square equal, and now we will put here, so this is omega r 0 divide a4 plus omega m 0 divide a cube plus omega lambda plus 1 minus omega 0 a square. So I will not put this dependence on t, it's understandable. So this is equation for multi-component universe, model of universe. So what we can see from already from this equation, we can see that the right side can already tell us about the history of the universe, because we can see that if, for example, we go in the past, so it means that when we go to the past, it means that scalar factor decrease. So let's put that a tend to 0. So this is past. Let's see me that everybody. Okay. Okay, so, and we see that which summand will win. Of course, the first summand will win. So we can see that the first summand, so R0 divided on A4, which will be much more than others, 2 and even 3, because we have a dependence as a cube or like this. So from this we can make a conclusion that in the past the radiation, so when we speak about relativistic matter, first we speak about radiation, and we will discuss what it means radiation, what it means photons, which photons we can consider. So, and we can see that in the past the much more energy density was related to the energy density of the radiation. So let's write this: radiation era or stage. So radiation won at this time. If we will go in the in the future, so it means that scale factor, let's put it, consider to the case when even k equals 0. So let's put it infinity or very large. We can see that in this case, omega lambda win more than for example the matter and radiation. So we can see that it will be in some relative future. We don't know which future, we need to investigate it when. So the lambda term, let's put it, will win. So and we already can, since we and of course some a which some value of a which between the first case and the second case middle. Don't remember. To alien, not. Let's just a second. Middle with one L or two. Now I start to think. When I type, I didn't think, but when I write, I already start to think. Okay. A, so we can see, so between, let's put like this. Between these two cases, between past and future. Okay, so we will have the situation when omega matter will win. So since this summand will be important. So, and we can call this, and usually it's called this as a mater era or mater stage. About you, we also of course have this summand, which is related with influence of the curvature of the space. And as you remember, we obtain it just again from the Friedman equation for the present time. And from the observation, we can write like this. Observation. We know that, and we will, if we will have time, we can speak about this. That K, which is again, I will remind signum of scalar curvature, Gaussian curvature, the same K sign of scalar curvature. So we know that K equal 0. So we can put here some some sign to remember about this. Of course, for now we discovered that, and to prove this from observation, to obtain this from observation, that really the space has a curvature equal 0. This is different independent measurement, which is not a simple one of this. This is investigation of cosmic microwave background with space satellites. It was a 3 space telescopes, great telescopes, which really change the understanding of some things which are related with the formation of structure. And of course, this is not simple, because in principle we understand that to prove and to investigate how we can investigate that the curvature is not 0 or 0. So we, in principle, we need to take 2 or 3 objects, for example, to build a triangle, and to be sure that the sum of the angle correspond to Euclidean, to the result of Euclidean geometry. If this is not correspond, then for example, the triangle like this, so, and the sum of the angle more than 180 degrees, so it means that the curvature is a positive. If this like this, so the curvature is a negative. And if this is exactly like this, so equal 180 degrees and 3 degrees, it means that curvature is 0, so 0 value. And of course, it's understandable that it's complicated to measure. You can't choose 3 galaxies and to make a measurement so using these 3 galaxies. So this is really such a, how call it, maybe not direct proving about curvature of the universe, but enough precise. Of course, we can't say that in the future the situation can be changed in the sense that we can discover something new. But for now, in recent lambda CDM cosmology, when we speak about this, we consider that the curvature, and you can also add here, so in recent model of the universe, so we consider that curvature equals 0. But it means also that the summand which we have here, okay, this which is related with the k, I will remind you and look by myself. So you remember that we obtain this from this. We instead to put k c square blah blah blah. So we expressed this through this value omega 0 minus 1. So this omega 0 minus 1 come to us from analyzing of the Friedmann-Lemaitre equation for the present time. And if k equal 0, we understand that omega 0 equal unity. So, and we can remember about this because if k equal 0, we have that omega 0 equal 1. And it means that if we will put the sum of all components, it means that omega r, so radiation of the present time, plus omega matter of the present time, plus omega lambda equals 0, or equals, sorry, equal 1. It should be equal 1 since we have this from observation. And we understand also that if really we can estimate the part, the influence of the radiation in the universe on the present time, just calculate all photons in the universe, for example. And we can also, in principle, calculate all matter in the universe. In this case, we can obtain the value for omega lambda, because it will be 1 minus omega radiation for the present time. Sorry, minus omega matter for the present time. So to justify this request that we need to have curvature equals 0. So this we can also put in some frame. How, for example, we can estimate the value of the relative energy density or relative density in the total of the universe. Okay, so now we will consider which equation and which solution we can obtain solving the Friedmann-Lemaitre equation in this form. In this form, I can put here. Okay. So we can we can keep for a general consideration, we can keep the summand with the curvature. So just to consider the problem in more general case. So since the Hubble parameter is a point divided on a, so we from the left part we will have a point divided on a. Sorry, a point divided on. I would like a square immediately to multiply on the right side. In this case, I will Let's try this one. Okay, h0 we will have square. So, and after this, this a, I will multiply, I will move on the right side. It means that I will have omega m. Okay, let's start from radiation. Radiation 0 divide on, it was 4 became square plus omega mater 0. It was the first power, so it will be a. Plus a square omega lambda, and let's call just for convenient we can call omega k equal 1 minus omega 0. So it's really looks strange that it looks like we have density of the curvature, energy density of the curvature, but we just using this as a notation. So, and we will not put some sense in this energy density. In any case, since other terms has a representation of influence of this of the total energy density, in principle, it looks like this. So I just want to put here plus omega k. So this is what we have, and what we want to obtain. We want to finally to obtain the dependence of a scale factor as a function of t, to see how universe will evolve. So since a point, this is a derivative of scale factor on the time, we will have, so you rewrite, I will do like this. I kill here square. I will put here 1.5. So a point equal dA by dt. So I understand that I will have from the one side h0 on dt, but look, I will integrate the right side from 0, so from the beginning of the appearing of universe, I can tell like this, and to some scale factor a. So in this case, I can put here t, and here dA, and on all these beautiful things. Okay, I will repeat it. Plus omega m 0 divide a, plus a square omega lambda, plus omega k, minus 1 divide on 2. Okay, because we need to divide. So again, what we discovered before, the same, of course, we can see in sense which summand will be important on which time, and we can schematically to write, it's convenient, so to write the evolution of the universe. So if we will consider the scale factor, it means that we can divide the evolution of the universe on 3 stages. This, let's put it here and here. Okay, so it means that in the past it was okay, let's call it predominance of radiation and I will put here the condition that epsilon radiation much more than epsilon matter or epsilon lambda. After this, the stage, it was a stage, I can call it even, sometimes it call, let's put it, radiation era. Okay, so after this, it was a time when the stage or era which is related with predominance of matter, baryonic, not only baryonic matter, we will consider dark matter too. So it means that epsilon matter was much more than epsilon radiation, epsilon lambda. And this call don't have enough place, so I will correct it like this. So, and this call matter era. So after this we have, and what is important that this is A, there is a special, as we understand, special moment which correspond A, and we will call it Rm. So exactly the scale factor which correspond to the passing from radiation era to matter era. So which corresponds sometime Rm. So it was really in some time before, in the past. We understand that the next stage of the evolution of the universe, the radiation, as a matter era, finished in some time, should finish in some time, which correspond to the scale factor, and we will call it M, and I will put here lambda, because we already understand that in the future this summand will win. So, and we call it predominance of let's call it predominance of lambda term, or in general it can be called as a so we understand when omega lambda will be more than omega epsilon. We could put omega 2 r or epsilon matter. This era we can also call as a dark energy era. So, and the moment and this corresponding scale factor which tell us when it was or when it will be, this we will call it AM lambda with corresponding T time M lambda. So why I tell about this era as a dark energy era? In principle, we can put as an additional component, and we are not sure completely that this is exactly only lambda constant. So now there are different models which consider different kind of energy, which can which influence on the evolution of the universe such a way is that the space expand exponentially. So this is a key point. Oh, sorry, even to say better, the universe, the space expand with acceleration, not with a deceleration. And as you remember, Friedmann-Lemaitre equation for acceleration of scale factor really tell us that if the equation of state, we consider the equation of state like this, and if double V less than minus 1 divided 3, if I remember correct. So because we have, yeah. So in this case, we will have the effect of acceleration of space. There are also now the models which consider like a phantom energy. So it means that this is not exactly lambda constant with a double V equal minus 1. Minus unity, but it can be also something which is different from unity, but something different kind of energy. But in any case, the main property of this form of energy to create the acceleration of the space. So why we call this dark energy era? When we speak about dark energy, we include not only lambda term, but we can consider also something additionally. But again, in standard cosmological model for now, we consider that for this acceleration, lambda term is responsible. So this is the evolution of the universe. But of course, in dynamical cosmology, we need to find exactly this time. And what is also beautiful that we can use for much to simplify the consideration. Okay, in principle, you can integrate, consider to integrate this equation for total numbers, which we in principle can know from observation. But it is more convenient to use one component models of the universe. So, for example, on this era, radiation, I will call it this. So the first one, radiation era. So in radiation era, we understand that it will be much more important the first summand, and we can write immediately that H, put here blue, okay, H0T equal integral from dA. So it will be 8 divided on square root omega R0. So, and we can integrate it, and in principle, we can finally, so it's a simple integral, we can finally to obtain that the scale factor will be, so what it will be, so we will have a square finally, it will be square divided on 2, so 2 we will have.
I'm sorry, why we have this term in integral?
Sorry, say again?
Why we have this term in integral?
Because look on this equation, you can see. So, and if I consider radiation error, I can consider that this is small, and this and k equals 0. So in radiation era, I can consider that omega r 0, not 0, omega r more than omega m and omega lambda. And I will also consider that omega k equals 0.
Okay, I understood this.
In this case, yes, you are
okay,
right. The
okay.
equation, yes, I need to write like this, of course. Yes.
Okay.
Yes, your question was completely correct, because yes, in this case, I need to put like this. In principle, yeah, and I put here from 0 to a, but I need to remember that in this case, let's put me here, that a should be less than ARM. So we exactly in this time. And for example, we are in the era, in the radiation era, and we would like to understand how will evolve the space. And why it's also important, because when we, for example, if we can reach the object, because you understand that when we consider the object which are far from us, so this object, of course, the emission from this object need to spend some time to reach us. So, and the electromagnetic wave come to us during a lot of time. And this radiation, of course, also fuels the expansion of the space. And we need to take into account this. This is one point. Of course, when we speak about radiation era, this is special era where no stars, no galaxies, nothing. So we will see that radiation era says about very high temperature, where we don't have yet the structure which we can see now. So, okay, let's finalize this equation, this expression. So it will be 2h0 square root omega r0 1 divided on 2, and time will be like this. Okay, so it means that the scale factor proportional in this case as the square root of time. So this is a dynamical representation of how the universe evolved due to evolution. Second. The second equation, so we consider, when we consider radiation era, when we consider radiation era, this is to understand what exactly we consider as a radiation. So, which kind of emission we need to consider. And so, omega radiation. Omega radiation also consists of some components. In the first, what we need to understand that this is all photons which come to us from the stars, from all objects which product the emission. Doesn't matter from radio band to gamma ray band. So let's put here omega stars. And let's consider it for the present time, for example, to estimate it, because you understand that for example, to calculate exactly the scale factor corresponding to some time, we need to know exactly omega r. So the second component, this is So this is all stars. All stars plus gas, everything what we can see. The second component, this is very important component, we call it CMB. So this is, as maybe already discussed, we can CMB. This is cosmic, microwave, background. We use in post-Soviet Union space, we used call it as a relict emission. So, but now in international community and cosmological and astrophysical community, we are using cosmic microwave background. So cosmic microwave background, in the beginning of our lectures, we considered that this is photons which come to us from the hot past of the universe. So the concentration of these photons is like 401 centimeter cube. And it's distributed homogeneous and isotropical in the space. And these photons appeared due to, on this stage, again, I will put here like something, you know, so we consider radiation error. Their product and temperature of this emission 2.7 Kelvin. So, but when we go in the past, yes, and we will find the correspondence between temperature and scale factor. So this temperature was bigger. So this emission larger. This emission these photons, they are product of different nuclear reaction between particles on the early stage of evolution of universe. So, and in some moment, very important moment, and this is in vicinity of, I will put here, in vicinity of this time, it was very important moment when this emission became free. So if before these photons connected with the matter, with a scattering like this, so and the universe here was thermodynamical equilibrium. So it means the number of ionization processes was equal to the number of recombination processes. So, and but in this photons appeared with a different of reactions. Starting from some time, these photons became free, so they can distribute without often connection with the matter. Of course, there is a connection with the matter, and we will discuss it. So this is the second very important component of emission. And the third one, this is neutrino, because neutrino are these relativistic particles. They have a mass but very, very small. So, and we also need to take into account this in principle. So let's put here neutrino 0. There are neutrino which come to us from the direction of the sun. So electron, muon, and tau lepton neutrino, 3 kinds of neutrino. And some years ago, it was, as I remember correctly, it was given as a Nobel. This I remember correctly, of course, given a Nobel Prize. I don't remember exactly which year, for the proving that neutrino can change. So, for example, you have a electron neutrino, and they can move in tau lepton, for example, neutrino. Some changing of the sort of neutrino. This tells us that neutrino has a very teeny of mass, but in any case, they have a mass. Sometimes, and when, for example, we speak about hot matter, sometimes, and sometimes before, it was considered that possibly for the role of dark matter can pretend neutrino, but now we are sure that this is not neutrino because it's not enough to explain the data, the observational data. In any case, we have also neutrino. And also this neutrino, there are relic neutrino, which also come to us from the past time of the universe, because again, due to the different reaction, nuclear reaction, the neutrino appear as a product of this reaction, not only photons, but also neutrino. So, and in principle, we can estimate how much energy this neutrino can give in this stage. So what is important that this is three components of physically of three components which give which create the total energy density for the radiation. Okay, so, and it's convenient to estimate which exactly we need to take into account. So let's do it. And the first, I would like to speak about cosmic microwave background. So in principle, we can estimate the energy density of cosmic background for the present time. Shortly, we just will use the CMB. CMB, it means cosmic microwave background. Okay, so how we can estimate I will for the epsilon, because I also need to estimate the critical energy density. So I can consider this the energy density as a alpha multiply on T in 4. And alpha, this is the constant of density or emission density. So this is this alpha, we know this is constant, fundamental constant, and it is as a 7 with something like a 5 multiply on 10 minus 15. We understand that so the dimension should be erg divided on centimeter cube K4. So I like to write this when we make some estimation of energy or density energy. I like to use mega electron volt, because it's allow us not to work with the very small values in this case. So, and I will from erg to electron volts. So I will remind that 1 electron volt equal 1. We already used it once, I remember, 2 times. So, but I will remind erg. Okay. So, and understandable that 1 mega electron volt, we also will use it in inflation stage, 1.6 10 minus, so we need to multiply in 10 in 6 erg. If we will recalculate this constant in mega electron volt, and also to kill some others, so and we'll consider as a mega electron volts divide on meter cube Kelvin 4. So if you will recalculate all these orders, you will see that you finally will obtain 4.7. I don't want to spend time to make these simple calculations of the numbers. So it will be 4.6 multiplied on 10 in minus third. Now I want to calculate epsilon CMB. It means that I need to put this alpha on temperature CMB. I put here, of course, 0 because for us it's fundamental to understand, and you can see what is beautiful here in the expression for the scale factor, that to find the scale factor as a, I mean, to find the correspondence between scale factor and the time, we need to know only omega R0 because this is here. So why for us it's interesting to recalculate the energy density, relative energy density for the present time. So I put here 0. And TCMB 0 equal 2.7 Kelvin. And if we will put it together, so what we have, it will be approximately 6.3 mega electron volt meter cube. 0.3 or 0. I even look on my, it's like, to be more precise, will be 2.6. So like this, between 2 and 3. So this is energy density of the CMB, energy density for the present time T0. Of course, we can immediately to see that if temperature will increase in the past, so energy density increase also. But we need to obtain omega R0. For this, we need to estimate epsilon C0, which is we obtained before. I just remember this by heart. So this 3c square h0 square divide on 8pg. C is speed of light, g this is gravitational constant, h0 this is Hubble constant. So this is parameter of Hubble on the present time. We already calculated it before, and it's around 10 minus 30 gram on centimeter cube, like this. So we also discussed this density is very low. So I just want to put it. You can put here the all constant. C this is 3 multiplied on 10. The end the 10 and 10. So I will not put it. So I think you know this constant G. This is 6.67 multiplied on 10 in minus 8 H0 for H0, it's enough to use the value which we decided to use. It's 70 kilometer per second divided on megaparsec. If we put everything in this, and you will recalculate also mega electron volt, you will obtain mega electron volt divided on meter cube. So this is value of the critical value of the energy. Now, if we will recalculate omega C MB for the present time, so we need to just divide epsilon C MB for the present time, divide on epsilon critical. We put here 0 because it's correspond to H0, just to remember that we obtain it from this, okay? So, and so if we will divide one of these two numbers, we will have approximately 5 minus 5. Right? So 25 divided on 5, we obtain 5, and 2 order and 3 order. So this is value of estimation of the energy density of cosmic microwave background. Let's consider, but okay, if we will look on the number of the stars, of the all photons which created by all stars in the universe. In principle, we already estimated it before, because and just consider who will win for now the emission from all stars, all galaxies, or during all time of the existing of the universe, or microwave background, or these photons which distribute homogeneously in the space. So to estimate of the omega stars, okay, for the present time, even no omega yet, because we will estimate, the first we need to estimate epsilon stars. Sorry, stars. 0, okay. So what we need to do, we need to multiply the concentration. So we can consider that, let's consider that all stars are the same, with the same luminosity, just to make a mean estimation of the energy density. This is concentration of the stars. We will multiply on the luminosity. I will remind that luminosity, this is energy by dimension. This is energy divided on time, so power of emission. So n multiply on L, we obtain epsilon divided on T. So we need to multiply also on T. And if I want to estimate all photons from all stars, which was produced during all evolution of the universe, even we now don't take into account that maybe the stars didn't exist some times ago. They created, they died, they again created, and like this. So in any case, I will put it here. So it will be T0. This is the universe age. And it will be the high limit for the energy density of the stars. And we know now everything about this one. We already discussed. we already discussed this value, which we can obtain from observation. You just, use some volume of the space, and you calculate in the scale of 100 megaparsec, where cosmological principles start to work. You calculate the number of the galaxies or cluster of galaxies, and in principle, you can estimate the mean density. So concentration, for example, and L we know. So, and we speak about that this is approximately 2 multiplied 8 solar luminosity divided on megaparsec cube. The age of the universe we also know approximately. So this is like 15 or 14 billion years. We will calculate it more precisely, but for now we principle estimate this is at least 14 billion years. So if you will put it together and calculate it, you will obtain the very, again, I like mega electron volt. So we will obtain 0.007 mega electron volt on meter cube. So we already see that, and okay, yeah, let's consider omega star here. So which is epsilon stars 0 divide on epsilon critical 0. So divide 1 on the second, so we will obtain finally very small value. So this is 7 multiply on 1, 2, 3 minus 3 divide on 5, 3. So this will be approximately 10 minus 6. Yes. Let's put it because. So we can see that, and let's consider with this one. So we can see that cosmic microwave background, we can see MB0 more than omega stars. So this is like a proven that if we calculate all photons from all stars which product during, and this is a high limit, because in principle it's not completely right to put from 0 to T0. So, but if we calculate all photons from all stars, we can see that it's not enough to make really some very important, very to work for now, very how to call it? Okay, of course, very important contribution in the total, in the energy density for emission. So we also can, we already need to finish. Just I will quickly to write to finalize that we also can to recalculate the number of neutrino for the present time, and this is much more relativistic neutrino, relic neutrino. It should be 0.68 omega CMB. CMB would give now the data. So this is 3.4, 10 minus 5. So together we can, and this is also less than CMB. In any case, to finalize for today, we can write that the omega radiation for the present time, this is omega CMB for the what we need to take into account, plus omega neutrino. So this is a component of the radiation for the present time. So we can estimate, and after this we can estimate other things. All together, it will be a probe. So it will be together for 8.4 multiply on 10 minus 5. So this is contribution of the emission for the present time. So on this we need to finish. For the tomorrow we have the next lecture. So tomorrow we will estimate. We also will speak about baryon matter and dark matter, and we will find exactly this time, important time in the history of the universe, this time and this time when we have a change from passing from one era to another era. By the way, we will discover that now we are waiting in the dark matter, dark energy era. So, and yeah, looks not beautiful that in the future it will be dark energy era, but in any case. And so we will find the crucial expression for the evolution of the universe. So if you do have some question, I will make now a screenshot of your presence. Questions? You can ask question, be brave. I'm sure that it's normal that something is not understandable. So no questions. Okay. So in this case, we will meet tomorrow. Okay.
Okay.
Thank you.
Thank you. Goodbye.
Goodbye.
Goodbye.